webinars, the most ambitious one yet, as we've just found out. So this is about tackling COP26 challenges using digitalized surface manufacturing, presented by the EPSRC Digitalized Surface Manufacturing Network Plus. And I will begin with an overview of the DSM Network Plus and its relevance to COP26. You can all hear me, hopefully.
Yep.
Okay, so the Network Plus is a £1 million investment by the EPSRC to bring together the diverse expertise and capabilities in UK academia to enhance digitalisation in surface manufacturing, to move the sector forward to meet the Industry 4 challenges. And this is being done in collaboration with UK industry, including with members of the Surface Engineering Leadership Forum. Just a few words about the importance of this sector. The Knowledge Transfer Network carried out a study, a so-called special interest group study, into the surface coating sector, and it presented a report, and it confirmed that the value of products which are directly affected by coatings is over 140 billion, and those 140 billion pounds worth of coatings contribute to industrial turnovers in excess of 380 billion. So it's a very, very important sector. And to that, we add the findings of the Made Smarter review, which is a government review 3 years ago now, which said that if industry adopted digital technologies, it could benefit by up to 455 billion over the following 10 years. And the other thing you can see to the right is the sectors that are affected by coatings. All of the main industrial sectors, like automotive, construction, oil and gas, aerospace, transport, etc., are critically affected by coatings. The products wouldn't function without coatings. The total value of those coatings is around 11 billion. So you could say that 11 billion pounds worth of coatings in the UK directly impact 140 billion pounds worth of products and turnovers over 380 billion. So it's a bit important. In manufacturing, digitalization has been shown to be very important. If you do a Google search and you put the 7 wastes or the 8 wastes, it will give you diagrams like this. And they talk about the digital gap. And by filling the digital gap, you can reduce overproduction, reduce inventory, reduce transportation, reduce motion, reduce weighting, reduce defects, reduce overprocessing. By doing that, you increase the value added, or you increase the productivity. And you do this by better utilization of assets, reduce dependency on tacit knowledge, reducing the time and cost linked to product verification. You improve and give visibility to all business performance metrics like yield, right first time, cost, delivery, quality, and equipment effectiveness. You enable and improve design for manufacture. You open up new business opportunities, and basically you provide a framework for developing a more resilient business and sustainable manufacturing. Now, one thing that digitalization helps with is creating what's called an intelligent manufacturing pathway. So we can do things like developing digital twins of processes, a software-based model of the manufacturing process. So if this black line is your manufacturing process in digital form, you can interface with your manufacturing process through so-called cyber physical devices and monitor against the digital twin and make sure that you're following the desired manufacturing pathway. So that's just one benefit of digitalization. So hopefully you all believe in the benefits of digitalization. The other thing to mention is that coatings are particularly significant when it comes to sustainability. They allow scarce materials to be conserved, so you don't need to use the scarce material for the whole bulk. You just use it at the surface. You reduce energy usage in transportation by reducing friction in vehicles, by making aircraft more fuel efficient by using thermal barrier coatings. You can improve power generation efficiencies, such as in ground-based turbines and wind turbines. And if you do an appropriate selection of your coating, you can avoid the toxic effluents which are associated with many traditional coating techniques. So if we just focus on energy, surfaces and coatings, particularly vital in energy, they help in energy generation and conversion, they help in energy conservation, and they help in energy storage. So just running through these quickly. Energy generation and conversion, things like tungsten carbide cobalt coatings on gas and steam turbines, organic coatings for corrosion protection in solar water systems, for example, anodizings for enhancing corrosion protection on light alloys used in various structures, coatings used in photovoltaic devices. Obviously, these are photovoltaic devices are basically multi-layer coatings, and coatings are intrinsic to fuel cells as well. In reducing, in energy conservation, things like solid lubricants are used in machinery, solar control coatings are used for architectural glass, and polymer coatings are used to control building temperatures, for example. And in terms of, I don't know what happened there. In terms of energy storage, lithium-ion batteries are multi-layer coatings, hydrogen fuel cells and membranes are basically comprised of coatings. So coatings are absolutely vital. In engines, they are used to reduce friction, to reduce so-called harmful sulfur and phosphorus additives. In oils, you can get higher power energy densities, use alternative energy materials. You can get zero emissions by having things like exhaust gas recirculation technologies, and all of these are coatings. So you're all going to say, okay, that's an internal combustion engine. That's not what we're interested in anymore. However, these coatings and other developments enable things like gearboxes to work more effectively. So they have longer fatigue lives, they have a higher fatigue threshold before they start to show fatigue. And therefore, we can start to make gears smaller and lighter and more efficient. Of course, these are important in electric vehicles as they are in internal combustion engine vehicles. So all kinds of gears can be protected, more efficient, last longer, reduce abrasion, reduce pitting, fracture and seizure, etc. So these are very important in not only in engines, but in things like wind turbines. And there's a lot of work going on now. You might remember when wind turbines first came out, people said they were failing after a few weeks because the gearboxes failed. That's not happening now. And that's due to even to fossil fuel companies like BP are working very hard on extending the lives and the reliabilities of wind turbine gearboxes. And now they're very efficient. Okay, just moving on almost finally to telling you about the DSM. The network acts between the academic activities and the industrial activities. So what it does is it brings together academics together with industrialists. We fund feasibility studies and industrial demonstrators. We have a very heavy involvement of early career researchers, and we pull through the academic developments to the benefit of industry. We also address societal challenges like the Sustainable Development Goals, which we're talking about today, climate change, green manufacturing, healthcare, and biosafety. The network has a strong social media presence. We're on Twitter, we're on LinkedIn, we've got our own YouTube channel. All of the webinars that we produce are on our website, which is here. And we are expanding our horizons. We originally started with 27 members and 16 organizations. Now we have about 400 members and 64 organizations. And we're also expanding not only in the UK, but worldwide. We realize that not all the important developments and research will happen in the UK. So we're linking into research centers in North America, in Canada, in Europe, in the Far East, and in Australia as well. So that's me giving you a quick intro to the DSM. You'll notice that interspace through the talks, we have a number of talks from PhD students. And what we realize is that the future, well, first of all, our young researchers will be the people who have to deal with climate change. And also very often they are the brightest, and they can see the new ideas and come along with new ideas for us. So we're ageist in an inverted sense. We're very much in favor of young researchers. So they're very prominent in these talks. And the first person is going to be Caaisha, out you there, is going to give a first-year PhD student's very quick view of what COP26 is.
Yeah, sure, I will do that.
So can Caaisha share her screen?
Yes, I can, but I need you first to
Allan, you can
share yours.
stop sharing yours. And then...
Yeah.
Yeah. Good morning. My name is Caaisha Warsame from London South Bank University, and I will be presenting to you the Conference of Parties 26, abbreviated as COP26. A quick background of COP. It all started back in 1995, where the first COP1 took place in Berlin. Fast forward 26 years later, we have COP26. Why COP26? Well, prior in 2015, the COP21 took place in Paris, where every country agreed to work together to limit global warming to 2 degrees and aim for 1.5 degrees. Then the Paris Agreement was created. However, half a decade later, although progress have been made, but the commitment laid down in Paris did not come close to limiting global warming to below 2 degrees. And the window for achieving this is closing. Hence, this resulted for the past few months for developed and less developed countries to experience severe climate change. Today, we gathered to find an alternative solution to this matter. The objectives of COP26. Well, first, net zero and 1.5 degree climate change must be achieved, which is countries to prepare with the emission reduction target, nationally determined contribution, known as indices plan, introduced back in COP21 must be done. Then to accelerate the phase out of coal, to encourage investments in renewables, and to speed up the switch to electric vehicle. Then to regulate to protect natural habitats and communities. Third, to mobilize finance, which is the promise that was made by developed countries to deliver $100 billion annually must be reached before securing global net zero. And lastly, to work together to deliver. What will happen at the UN Climate Change Conference? Well, more than 190 world leaders will attend the conference at Glasgow from the 1st to the 12th, where the UK together with Italy will host a UN climate change conference. They will review the Paris rulebook known as the Paris Agreement. They will set out how much they have reduced their emission, and lastly, to achieve the objectives of COP26 before the year of 2030. I believe progress is impossible without change, and those who cannot change their ways cannot change anything. Thank you very much.
Thanks very much, Caaisha.
You're welcome.
Very useful. Okay, we're going to move on now to the next speaker, and the next speaker is Laura Sands, CBE. Laura is a non-executive director of SGN Limited, is involved in the energy systems Catapult, in the energy systems for the future, digitalized decarbonisation and decentralisation. I first worked with Laura more than 30 years ago, and when I was at Hull University, and she helped us to convince politicians and decision makers about the importance of surface engineering. So she actually is quite steeped in surface engineering from, as I say, more than 30 years ago. She was, of course, very, 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 very young. And I wasn't quite so young. And I think I'll pass straight over to you, Laura, if that's okay.
Allan, thank you so much. And Caaisha, thank you so much for your introduction on COP. It's a great pleasure to be here, and it's absolutely wonderful to be with the surface engineering community again. I'm afraid I'm a little bit out of touch, so I'm going to be really focusing on the energy and digitalization area, but you'll see so many opportunities here for surface engineering to absolutely drive things forward. I think Caaisha was very clear, time is running out. But we are having a very fundamental change to how we look at our economy and how we look particularly at the energy system. So this is, in the middle here, you could say, is Boris Johnson, and he is looking at an old-fashioned energy system where big is beautiful, command and control, to an unbelievably dispersed, distributed system where one has data right at the heart of it. Location is absolutely key, with differential energy systems depending on your location. I can't do much without a bit of Monty Python, so blessed are the cheesemakers, because actually what we've got is lots of smaller companies getting involved, innovating and changing our system from one that was absolutely centralized to one that is distributed, hopefully democratized, but certainly digitalized. And so what does the future look for us in the energy sector? We need a very different economic driver. It's not consumption, it is optimization, which is at the heart of surface engineering in many ways, and Allan's points about productivity. We're going to have 50 million actions, or probably more, 100 million actions and assets on the system. And we've got to start really capturing some of the productivity gains and what I call the decarbonisation dividend, because there really is one. If you look at what happened to data, in 1990, a terabyte of data was $1 million. Today, it's probably 0.5 cents. That is what's going to happen to the commodity of the electron, despite the fact that we've got horrible high gas prices today, but that's the sort of movement. But let's be clear that if we don't get this right and we don't do it fairly, the citizens do have a veto on net zero. So what does net zero really mean? As I said, it's optimization, not consumption. It's going to look at new processes and assessment. It's going to, in many ways, bring forward new business models, which again drives opportunity for surface engineering. But what we have to do, and what COP must deliver, is an acceleration of decarbonisation, delivery of the true value of a new decarbonised system, reward customers and unlock that investment. And so we frame the new energy system as I said, optimization, not consumption. And we have 5 key drivers. We need to drive out carbon, reward customers, reduce whole system costs, maximize capacity on the system, and unlock that capital. And you have a huge role in driving out that carbon, reducing whole costs, and also maximizing capacity through all the work that you do. So I'm going to give a little bit of an overview of the energy, data and digitalization task forces, what they're trying to achieve, and whether there might be analogies to the manufacturing sector, to other sectors, the transport sector that you're all operating in. So we are moving, as I said, from very much command and control system to a very decentralized system. Now, currently, the energy sector is run by 400 people, more or less, all of whom who know their each other's golf handicap, right? So this is a very, very small little club. We are moving to 100 million actions and assets, because if you think that every single EV car can do two things, every heat pump can do two mechanisms, this is turning the whole system upside down. And as a result, efficiency, productivity needs to be delivered right across the supply chain. It is no longer just a sort of pipe into which you as consumers are the sort of the victim of the system. This is going to be a very, very interactive. Now, if you do this in an analog way, it's going to fall over. So the data task force was very much around, this is at the bottom here, was very much around data visibility and infrastructure and asset visibility. The digitalization task force, which we're in the middle of, is really about optimization, about AI, algorithms, dynamic digital markets, and how that will actually bring the base of visibility of the data to life and to really optimize the system. These are the changing nature of interactions in the new system, which requires visibility, knowledge, analytics, and algorithms. And again, by digitalizing what you're doing, you're going to start to unlock the opportunities that the supply chain requires. Location, customers will have different changing needs. Data will be required by a whole load of new actors in the energy system, from property owners to transport companies. In many ways, the silos of all our sectors are becoming very, very blurred. And then you also have network systems where, particularly with following on what Allan was saying, dynamic constraint management, you know, this is going to be a very, very different, we are going to have to manage capacity in a way that we used to worry about commodity. And that's going to require a lot of innovation and a lot of changing in how we do things. And that's where your community comes in. There's also going to be a conflation between gas and electricity networks. I think you should really look at this whole issue around hydrogen as well, because your coatings are going to be very important in repurposing some of our gas networks to actually manage the different constituents of hydrogen. So digitalization of the energy system is not a nice to have. We will get collapse if we continue the way we do today. So currently, when the energy system is out of balance, somebody picks up a phone and rings up Johnny and says, can you ramp up? Now, we are now talking about hundreds of millions of actions and assets. This has to be done in a digital way. But that's not to say that there aren't risks. There's consumer detriment, there's system stability and security that actually does need to be addressed, and we'll be doing that through the digitalization task force. But the opportunity is transformative. It's not an enabler, digitalization. It's a transformer, and unless we actually look at it through that prism, we actually miss some of the opportunities. And it's not something that you just ring up your IT department to know how to manage Microsoft Word to sort out. So our job through the digitalization task force is about getting the plumbing right. We've currently got quite a lot of digitalization in the sector, but it's all disjointed. And our job at the digitalization task force is to create that very, very basic level plumbing, like HTML, like operating system, that actually allows all these exciting things to layer on top. But key to this is driving net zero and looking at carbon flows. So if you think this is our energy system and how we are trying to create the data flow, and so I call this, we need to create a data flow, a data with money, and with system need flow from what I would call prices to devices. So the offshore wind farm and the EV car needs to have a layer of interoperability by which each can work out its own needs. So if we've got lots and lots of wind, that's fantastic. That tells us that the EV car needs to charge. We need to then store and manage these systems in an integrated way. And to be frank, one of the most important things that doesn't actually exist yet is proper whole system carbon flows, which is going to be crucial for net zero. So huge opportunities. We've got a whole load of issues around millions of locationally varied actions. There are going to be new business models. There's going to be blended value. I have here a cow and cheese, because actually, if you're in the business of just a milk farmer, you're not going to make money. You're only going to make money if you become a cheesemaker. It's all about adding value. But very key to you is the operational cost reductions. I see surface engineering being absolutely crucial to driving cost out and optimizing the processes by which we move forward. But there is big changes, and there's a culture change. And the culture change with your environment in many ways is that you have to embrace the fact that engineering digitalization are very, very different culturally. One is about getting the right answer. Wonderful engineers on this webinar will want the perfect answer. Digitalization is about continual change. It's iterative, it's wrong, it reflects what it's got wrong and recorrects. And so it's a different mentality, and they have different investment profiles too. We do need to have digital literacy right across all our business and manufacturing, and we need to recruit new skills and experience. But in the energy sector, there will be a change in security and stability, because 100 million actions and assets will cause failure. We have to be able to contain that failure, not eradicate it altogether. So what do we want to be in the energy sector? We're pretty far behind. It's an old-fashioned sector. I like the PC mainframe journey, because I think that's really where we're moving, from that big IBM mainframe to designing everything around the PC. That is in some ways the big challenge for the energy sector. And we need to start designing things from the plug, not the power station, and then optimize the supply chain around those needs. It does need national assets, certainly the PC does, but actually it is designed around my needs. We can learn a lot from the food sector, and also on energy stability, we can also learn from the NHS. If I've got a headache, I go and pick up my paracetamol. If I've got a major problem, I go to the A&E department. But we must try and optimize the system at the lowest position possible, by which we can ensure that we create localized markets and localized opportunities. It is a real challenge, net zero, very, very exciting. But the energy sector is pretty far behind in terms of digitalization. We're trying to help take it on its journey. And I hope that, and I'm sure that surface engineering will play a huge role in that too. But let's not let the perfect be the enemy of the good. Thank you.
Thanks very much indeed, Laura. You can't be at the Q&A, so if anybody's got any quick questions for you, please post them as Saurav has indicated on the chat. You write about digitalization changing all the time, and it changes things in ways which you don't actually recognize. I don't recognize until people point them out to you. The best analogy, I was doing a course with our students on ethics the other day, and you know, the ethical dilemma of the autonomous vehicle. Somebody's got to decide, if it sees a pedestrian, it sees two sets of pedestrians and one of them it's got to hit. How does it make that decision? Does it, if there are 5 pedestrians there that it can avoid, and there's another 1 pedestrian and it can hit, it will probably just go to take out the one. However, it will instantaneously have a complete profile of every pedestrian. It would know their ages, it would know, you know, if one was pregnant or something like that. There's something that could affect the decision making. And I think this is one of the things about digitalization. The power of it is such that we can only really imagine. And, you know, people say that your washing machine's probably got more computing power in it than a mainframe computer had 10 years ago. So digitalization really does give us that immediate knowledge about energy usage, energy storage, and alternative energy. So now is exactly the perfect time, as we're seeing with, you know, with gas prices, I guess, and you know, how do we look for alternatives, and how do we, you know, store the energy is a big issue, isn't it?
I think there are two key points there. Well, one is the optimization of the system. If you've got 100 million actions and assets, you've got lots of options. At the moment, we've got 400 options, right? And they're all fixed and in many ways entrenched in their current contractual relationships. So if you've got 100 million, you've actually, despite the fact that everyone says, oh my God, this is very unstable, you've actually got more resilience by the number of people, right? Which is very, very good news, unless what you get is in some ways algorithmic failure, or in some ways contagion. So some of the things that's really, really interesting is if you put out a price that was a really exciting price for everybody to charge at that moment, you couldn't have everybody charging at that moment, because otherwise you actually change the profile and the system collapses. So I believe, and I'm not sure whether that's what we're going to come out of our digitalization task force, that we will be looking at algorithm regulation.
Yeah.
And that's going to be absolutely crucial, because knock-on effects are going to need to be in many ways managed. And that then comes back down to your point about which set of pedestrians do I hit, which is not a great option one way or the other. I think we're on a journey to learn how to manage these trade-offs. I think that there is actually, it's not each algorithm that's going to be the problem. It's going to be the interaction between different algorithms that are all machine learning at the same time. But none of these algorithms are static. That's the problem.
Yeah.
And so you've got this continual movement and iteration, which actually creates new results.
Yeah.
I'm absolutely putting my hands up. I don't have the answer. Anybody on this webinar has the answer, fantastic. But we do have to start to put some framework of regulation around this, where some of those ethical issues are assessed and, you know, in many ways monitored. But it is exciting, but with everything that's exciting, it's dangerous. I mean, we do remember that, was it Stevenson who was killed by his own train?
I think so, yeah.
Yeah. So, you know, what's called?
Well, we've got the challenges, but digitalization gives us the ammunition that we need to deal with those challenges. You know, we couldn't even thought of this level of digitalization a few years ago. It's, you know, it comes to mind the pandemic. You know, if we hadn't invented the vaccine, where the hell would we be? You know, so solutions come along in the same way that digitalization has come along, just at the right time. There's a question from Barbara. What is the role of digitalization in integrating renewables into our energy system, balancing harmonics, load, etc.?
Right. I mean, I think it's absolutely crucial, particularly if you've got all these different assets. And one thing that the energy sector is not very good at is learning from other sectors. So if you think one of our problems at the moment is storage, if you think about the food sector, before refrigeration existed in the food sector, you probably lost about 60% of the food that was being developed. If you think of refrigeration all the way through the system, we need a lot more storage in energy. So you've got frozen food, which is, let's say, hydrogen, salt cavern storage, that very long-term storage. You've got flash freezing, which is an EV car, which can move very quickly, but doesn't have a long period of longevity. But one of the really interesting things about the food system, that if you think about the energy sector, and that is, if we didn't have fridges in our homes, supermarkets would have to be 3 times the size they are today.
Yeah.
Right. So if you consider, if you have distributed storage, you actually reduce the overall cost and overall need of the whole system. And so I think one of the key components of digitalization will be creating the system need and price points by which storage is really starting to unlock and be a viable and important component of this system, because otherwise we're going to have to create milk lakes and butter mountains of electrons without optimizing that. And the storage area, I see a massive role for surface engineering and all the work that you will do.
I'm sure surface engineering is the answer to all our problems.
Everything, Alan, everything.
Everything. You know, just on the storage issue, when there was panic buying of fuel, people, apparently there was more fuel stored in all the cars in the country than there was in all of the fuel storage depots, which you know, you have to think laterally about things like storage, you know.
Absolutely.
And, yeah. Barbara, does this answer your question?
Yeah, yes, absolutely. And it was a really great analogy. Thanks, Laura.
Great, super. I think we need to move on. I'd like to thank you once again, Laura, for a really good starting talk there to bring all these issues into our minds. And you're right, in digitalization, we've got to think laterally. We've got to think about all the different impacts that are out there. So thanks again, Laura. If we could clap, we would. Right, so we're now moving on to Barbara, and Barbara's going to talk about decarbonized transport and the role of surfaces, which is extremely topical. So do you want to share your screen, Barbara?
Sure, thanks, Alan. Okay. Thank you very much, Alan. This is a really challenging topic because
your slides are not on my screen yet. I don't know.
All right, let me see. Are they there yet? Try again.
Something's happening. Great, super. Thank you.
All right, let me just get them full screen mode. Is that working for everyone?
Yeah, that's great.
Perfect. Thank you. I mean, I think just following on from Laura's comment and Alan's agreement that surfaces are everywhere and surfaces are critical to decarbonizing transport. And it was a real challenge in taking this forward because, as you'll see, there are a number of driving forces that are pushing us in terms of decarbonizing transport. We'll focus on that most relevant to COP26, and I'll come to that in a moment. But it really is a challenge because things are constantly changing. So if we just start at the very beginning. So this was, I'm sure you've seen this in many places. This is the grams of CO2 per kg for fleet, so for overall CO2 emissions. So this is a net zero approach. And as you can see, every country in the world is driving down and down at different rates. Many of these changes, as we know, are driven by legislation, and these are passenger vehicles. Again, you know, we'll focus on one or two topics here because it is such a vast area. But as you can see, the push down is going down to around 100 grams of CO2 per kilometer. The challenge here is that how do we do this, right? So at the moment, these are new vehicles. I'm going to make a little proviso here because I think net zero is a really interesting term. I'm sure we could go on and talk about life cycle analysis, right? So what is net zero in that biggest sense? Or in the case of vehicles, we could talk about zero tailpipe emissions. So these numbers are really taken as a whole fleet approach. So we may have some automotive manufacturers who have very high CO2 emission, tailpipe emissions from many of their vehicles, which they offset by a range of smaller electric vehicles. So it's averaged over the whole fleet. But here the driving force is to get down to about 100 grams CO2. And how are we doing that at the moment here? So I'm going to take you on a little road trip because I think the opportunities here are immense. So I've just highlighted, so the Automotive Council and the Advanced Propulsion Centre here in the UK regularly produce roadmaps to help focus industry on the directions and the opportunities that are available. So if we just look here, these are our standard internal combustion engines. Many people have mentioned, and particularly Allan was talking about how we might improve this. So we can look at reduced heat losses through coatings as one way. We can also look at reducing friction. Again, that will make our engines more efficient and more effective. What we also need to consider, and we'll go through all of this, is what is the overall way? How are we going to make this a more digitalized system? And that mainly comes through, and we'll see it in a little bit more. It's embedded in some of the later mode roadmaps, but it really is getting sensors embedded in understanding how these coatings are performing, not only how they're manufactured, which is obviously important, but also how are they performing in service. So if we have a look, we're going to focus on COP26 today. So there are 4 goals. We're going to focus on the first one here. So that's secure global net zero by mid-century and keep 1.5 degrees within reach. And Caaisha gave us a really great overview of the goals of COP26. And now we're going to look a little bit closer at them. So countries are being asked to come forward with ambitious 2030 emissions targets to reach net zero by the middle of the century. And we're actually experiencing that here in the UK. As someone who's living in London, we are getting increasingly lower and lower emission zones coming out from the central emission zone. I now live in an ultra low emission zone. So we're constantly being driven to really think about how we move ourselves around. And that may be by public transport and the ways that we're looking. So if we want to accelerate the phase out of coal, and again, that goes back to Laura talking about the whole energy ecosystem. Curtail deforestation, because that's a great carbon capture system, basically. And here's where we're going to focus on now. Speed up the switch to electric vehicles. So that's a specific, as Caaisha said, a specific COP26 target. And finally, encourage investment in renewables. So how are we going to start to look at the electric vehicle and the really critical role surfaces play? And again, Allan has mentioned 1 or 2 in his introductory, and we'll have a closer look at those again. So again, using the APC maps and just highlighting the only 1 or 2 places where surfaces play an obvious role, and I'll point out some where they're actually embedded, but not specifically mentioned. But as we look forward here, so here's the trend at the moment. So if we look at the black line with the discontinuity, although we saw in the first slide, the goal for engines or internal combustion engine driven vehicles is about 100 grams of CO2. By using hybrid technology, so that's strategy 1, we can push that at its maximum down to about 70 grams of CO2 per kg. If we look at electric vehicles, so that's now the line that's coming in to really push forward, we can see that we can really start to significantly reduce that down to about 10 grams of CO2. So electric vehicles are going to play a very important role in driving this net zero forward. So let's start by taking them apart one by one. So one of the key aspects in an electric vehicle is the battery. So battery technology is critical in driving forward electric vehicles. Here we can see that we have mainly new chemistries around electrodes. But again, in producing these chemistries and actually in implementing them, it is a coating process. We need to coat the anode and cathode, the copper and aluminium, in a way to produce these thicker and thicker, ideally, structures. But in order to do that, we really need to think about how we're going to surface engineer each one of these layers that we're putting down. Here's some really specific ones. If we look at here, we have separators. We want to obviously reduce the thickness to reduce the weight of everything. But we're also looking at oxidation resistance and heat dissipation. Again, that will have an important part of surface engineering in order to deliver those aspirations. Again, here for the collector surfaces, again, we need to think about how we're going to functionalize them in order to deliver what we need. And that might be by plasma treatments or laser treatments. And again, we might be looking at hybrid current collectors where we're using metal coated polymers. Again, surface engineering will need to play a critical role in delivering these. But more importantly, if we come back to what we were discussing at the beginning with Allan, it's really embedding this thinking into the way that we're going to produce these things. So we also, when we're looking at these surface technologies, at these coatings, how might we reduce their production by using things like digital twins to make more efficient and effective manufacturing cycles? But also, we really need to think about how are we going to recycle these structures. So I know COP26 is driven by the net zero, and here in this case, in that specific goal, is reducing CO2 emissions. But what we don't want to do is to have sustainability problems down the line. And I really am interested in mentioning this. I had an MSc student who was looking at batteries this year, and they coined the phrase, are batteries the new plastics 50 years from now? So again, we need to think about how, when we're manufacturing these layered, these coated materials, how we might be able to recycle and reuse them. If I look at the electric machines, again, a whole wealth of coatings. If we really want to look at thermal management in these machines, so now we're taking that chemical energy and now we're making it into electrical energy to drive our vehicles. We have electrical insulation materials are vital in these machines. So we need to look at various coatings for film insulation. Copper windings, again, we're looking at how we can coat them to get enhanced behavior in the windings. And again, when we look at the actual stacking of the very thin steel sheets that make up our laminations or make up our electric machines, is that the thinner they get, the more important the coatings and the way that we're going to join them for rigidity and for overall performance also become critically important. Again, we are really looking at those manufacturing, innovations using coatings and digitalization in order to produce reliable and repeatable laminations. So COP26 focused on electric vehicles, but again, as Laura mentioned, there are a whole other range of energy vectors, and these are being investigated at the moment. I think one of the challenges that we have here, so we're very used to hybrid vehicles at the moment, and things like, for example, regenerative braking have a very important consideration of surfaces to in that. But as we move forward, we can see that when we get to the mass market EV technology, we're just moving through here. What we really need to overcome is the charging infrastructure. So in parallel to that, people are looking at other possible vehicles, and those are things like fuel cell vehicles. So again, this is a very vibrant research area, propulsion systems for transport. And in parallel to the technologies going around energy storage and batteries, we also have the hydrogen cycle coming in. And if I look at fuel cells, again, huge opportunities for surface engineering. We need to look at the, the plates, and these plates are coated because they need to be durable and have long lifetimes. What we need to then do, and here's a great opportunity for digitalized manufacturing, is to scale these up to high value manufacturing. So let's move on. We know we can make hundreds of thousands and millions of AA batteries, many of which are used in electric vehicles. But fuel cells have new challenges, not only in developing the surfaces and coatings required for them, but also, more importantly, in their scale up. Again, we need to have materials tolerant to a range of commercial fuels, and Laura alluded to that in the way that she was talking about. If we want to take our gas pipelines and change them to hydrogen, coatings and surface engineering will have a very important role in that. Again, we're looking at degradation constantly in all of these systems, and degradation is often mitigated by coatings. And finally, we need to look at how we're getting this digitalization in through the control systems, and that may mean embedded software, embedded sensors in our coatings, and coatings are a great way to embed sensors. And then we need to look at that overall life cycle. How are we going to design systems, not only for manufacture, but also for recycling and recovery? The next stage that we have is another way of reducing CO2 emissions from vehicles, and that is through looking at their actual structure. If we can reduce the mass of something, we make it lighter weight, and therefore we need less fuel or less battery charge to move it around. And this has been an ongoing debate. Here's just the Audi R8, not everyone's car, but a good example of the use of a range of multi-materials. So in this vehicle, we have carbon fiber, we have aluminum castings, we have aluminum sheet. And in many vehicles, we have also a mixture of steel and steel sheets. Great challenge here. And if we look at the lightweight vehicle, all the way through this, and this is the most apparent one, is bonding, mixed material. How are we going to join the structures? Again, surface engineering will play a very important role in this. And more importantly, it plays a role throughout the whole manufacturing process when we're stamping parts, when we're producing carbon fiber composites, for example. Surfaces will play a really important role there. Again, when we're devising these bonding techniques, we need to think about how we will disassemble these for recycling, for future recycling. Again, that will drive the way that we're designing coatings, the way that we're manufacturing these systems, in order to look at the whole life cycle analysis. So in summary, I mean, I've just given you a very high overview, but you can really pick apart those maps and find more places than I've highlighted where surfaces and surface engineering, including coatings, will play an increasingly important part in developing new transport for the future. So COP26 focuses on the acceleration of electric vehicles and the global drive to net zero. But I think you've seen that this future beyond electrification shows the role of surfaces in things like fuel cell and lightweighting, all in this drive to reduce, to get more efficient transport. So that's my conclusion. And I just really want to reiterate that COP26 is really looking at reducing CO2 net zero emissions, but really there are many more factors that we should really be thinking about in our goal towards ultimate sustainability. So thank you very much.
Brilliant, Barbara. Thank you very much. Will you be able to join us for the Q&A?
Sure, I can. Yeah.
That's great. Right, I'm now going to pass over to one of my co-investigators to introduce Claus.
Thank you, Allan. Good morning, everyone. Greetings from the UK, and it's a great pleasure to kickstart this event with Laura Sens, followed by Barbara Shollock. I'm going to now introduce the next speaker, who is Professor Claus. He's head of the Department in Environmental Engineering at Denmark Technical University, who is going to show us wider prospects of one of the key issues, which is the availability of clean water as we head towards the problem of climate change. And so he's going to show us how we can use biomimetic membranes-based approach using surface engineering principles to filter and avail some clean water. So over to you, Claus. Please go ahead to share your slides.
Thanks very much, Sarah, and I will try the somewhat daunting task to share my screen, but let's see how it goes. I hope you can see my
we can see
screen now. Fantastic. Right. So thanks again for inviting me on this. This is very, very exciting for me to be here as well. We started out with energy today, then transport, now into water. So I guess in terms of COP26, we're addressing the goal number 2 about protecting communities and natural habitats, but it's even wider than that. I mean, you cannot really produce energy without also considering the water part, which is sometimes actually forgotten a bit when we talk about all these things related to power to X and other things. Water is somehow the hidden agenda, which I will try to highlight a little bit here. I'll also try to highlight how I see that composite surface materials in this embodiment of biomimetic membranes can be used in this aspect to really advance the water treatment. So basically what I'm going to discuss with you here and also share how we develop is these water treatment materials, permeable surfaces for water treatment. And we like to look back into nature. Nature have had a R&D department running for, 3 billion years or so. So maybe there are things that we can actually learn from how nature is doing things. It's not everything in nature that is, you can say, optimally designed for what we would like to use it for technologically speaking, but there are some aspects that are really worth diving into. And the one that I would like to highlight and share with you today is the use of these aquaporin channels. This is a very busy slide here, but I hope that you can see the proteins that are sort of spanning the membrane and actually making sure that it's very selective transport. And there are proteins that are only selecting water when they transport. And just to make things a little bit easier, let's just look at the water channel here. And while I'm starting the little animation here in a few seconds, what you can notice the little red molecule, the yellow molecule here is just a water molecule that's colored yellow so we can follow it. But here you can appreciate what is happening in these channels. It's a highly selective transport that will only allow water molecules, even single file transport at the narrow constriction site in the pore. And then if we sort of coerce the molecule a little bit, then eventually it'll come out of the protein. And this is of course nice, and this is where the digitalization comes in, because this is not just an animation. This is actually a simulation where we are in and actually investigate the forces at hand that are responsible for this selectivity, and actually also a very high throughput rate of these molecules. The crystal structures of these proteins came available in the early 2000s, and based on that you can then do these simulations. The protein itself was discovered in 1992. That came the seminal papers out and was awarded the Nobel Prize 2003 to Peter Agre. But if you sort of just have a little idea of how we use digitalization here, this is how we can then begin to really analyze in very high detail what is going on inside the molecule. And sorry for this somewhat jet-lagged formula at the bottom there, but basically this summarizes some of the physics that we use to capture what is going on inside these very narrow pores that actually turns out to have a remarkably high not only selectivity, but also permeation rate. So each of these molecules can transport up to 10 to the 9th molecules per second, which is actually very high compared to many other processes, and certainly orders of magnitude higher than standard materials for water processing, which I will come back to in a minute. So these things sort of got us to the point many years ago, actually, where I was sitting discussing with Peter Agre, discussing how can we actually translate this knowledge, because in principle we have a unique building block and to actually make highly permeable and very selective membranes. So should we somehow put that to work, and how could that be done? And that's something that has been close to my heart for more than a decade now. And one of the things I realized that, of course, not only for separation but also for sensor properties, you can actually learn a lot from nature. But if again, we just today focus on the water part of the story. If you sort of were to imagine that you, based on the simulations that we do, also the experimental data that we have now, they are hard to get, but and we're trying to get those pictures to match up. But the bottom line is that if you imagine that you could sort of create a perfect 2D surface of these proteins neatly stacked up, in a 2D array, you get to these very, very high permeabilities. And in membrane language, we like to talk about these A values. This is a very high value. And how can I say that? Well, I can compare with commercially available reverse osmosis membranes, which we can sort of take a state of the art of a highly selective membrane. And you can see from the numbers highlighted in red here that we're about 2 orders of magnitude higher than that in this hypothetical sort of biomimetic membrane. And that sort of spurred the interest in this. And people were very excited if we go back about 10 years about, whoa, now we can do this, we should really do this. And there were also some, I have to say, some claims made that are not entirely true, basically in those early days. Because one of the hard things to do here is really to upscale this thing. And here it's listed some of the attempts. And I would also, without offending anyone, say that I guess you also sort of represent failed attempts to how to scale this stuff up. Because the thing is that these proteins, they reside in these very thin biological membranes. Thin, I mean a few nanometers, sorry, thickness, and that is a feat to actually translate that very, very thin, nanometer thin film into something which is, square meters, for example, which you would need if you really want to go into the water treatment business. You need these large areas. Of course, you'll win something if the permeability is higher, but there are also things that are complicating the pictures there. But the bottom line here is that this is really the big challenge here. And the other challenge is that you would like, and why is that important that these things are so thin? That is because the membrane has to be very thin, because the proteins, all the inclusions, the stuff that is transporting the water in this selective manner has to be very short, because otherwise you will not have an efficient transport. And of course, you can use the proteins as some of the things that I have been doing, but you have also, probably some of you have heard about carbon nanotubes and also these more synthetic materials, graphene, other things. And they're all based on this concept: get something which is really narrow, but also very short. And that somehow collides with the idea of getting something which is robust and scalable. And that's basically sort of one of the big things that we have to solve in this in order to move ahead. And the reason why you want to go through all this labor and put all these small molecules into these films and actually make them very selective for water transport is because you want to break away from this trade-off that you have to do, which is illustrated in the diagram to the right, where you see the water perm selectivity. That's just a fancy way of saying that if you really have a lot of you want to have a lot of water going through the membrane, then that will be high on the y-axis, then you will have a low number on the x-axis. So basically, if you have a very selective membrane, you will not really get that much water through. On the other hand, if you want to crank up the water flux, then you lose out on the selectivity. And this is because membranes that are made today, they are based on a different concept, where it's basically differences in diffusivity that regulates how efficient these membranes are. But here we are separating these things. We're building these structures, proteins, channels, or whatever, in one side, and then we have the membrane on the other side. And by doing this, you can actually, at least this is the idea, to break away from this limit that is limiting current membrane technologies. If you're going to go into a bit more into the science, you would see that if you use lipids, for example, that's where proteins are born and raised. Those are exemplified here by this POPC, that's a palmitoyl oleoyl phosphatidylcholine. It doesn't really matter here. The point here is that if you want to have a robust film that you can put on top of something to make a good membrane, you will need to move to polymers. You will need to go into polymers, and they need somehow to look a bit like the lipids with hydrophilic and hydrophobic parts, but they need to be thicker in order to be stable. And that somehow collides with the idea that you need something which is short. So you are left with this issue, what I call the thickness issue here, because when you use polymers, and to the left of the picture here, you see these lipid molecules, these are the green ones, and then on the right, the top part, you see these polymers. And the polymer core, which is sort of this red area, these red segments of the polymers, they need to be hydrophobic, because that's how the proteins, and this is also will design your barrier properties. You will need a hydrophobic barrier, and then interspersed in that, you will have these very high permeable conduits for water. And that gives an issue, because when you want to make a robust film of, let's say, 5-10 nanometers thickness, then you have a mismatch between this very short channel and the somewhat thicker film. And this is one of those big issues that we need to solve And also, especially if you use proteins, you could actually pull the protein out of the functional state if you're not careful in designing these polymers. On the upside is, of course, that you could do a lot of interesting chemistry on the polymers, which you really cannot do on the lipids. And there are many other good reasons for choosing the polymers. But this is really one of the inherent challenges in this. And the next slide is really terrible, so I'll go through it quickly. But many years ago, I did some work where we actually looked at this and found out that the matrix in which you put this in, the polymer matrix, actually is to be basically sort of considered as a soft spring. You can think about like a mattress, right, where you have sort of dimpling or puckering down around these short inclusions. So it can be done. We knew that already 20 years back. It can be done to put these very short things into somewhat thicker materials, provided that you select certain classes of polymers that allow you to do this. But it's not impossible. And that was something that actually spurred us on to sort of say, okay, maybe we should actually try and do this. And we and other people have tried to do this. This is a recent review. And again, there's a lot of things going on this slide here. But if you concentrate on the left, you can see this is like a porine protein. In the middle section here is shown also these artificial systems where people should try to do things, 2D nanosheets that could be graphene, for example. You try to pack and to make surfaces, or you try to do things that are stacked up, or lamellar structures. That's also what is done with graphene in some cases. Or you can try simply from scratch to build a structure that will allow this very selective water transport, and sort of look a little bit back to the aquaporin, see how is it the aquaporin protein is doing it. Could we mimic something like this? Or can we make some kind of sponge-like structures, which is on the top, the bottom right? But then, of course, that may not be the best of ideas, because you will actually end up having these very long channels, which are then not really giving you the permeability that you would like to do. So I think this sort of nicely sort of encapsulates what are the issues at hand right now, or what are people trying to do. A lot of people are focusing on the proteins, but I think also more and more people are thinking about these artificial structures where we look a little bit back to the protein. But the bottom line is we still need to make this surface, this very special surface, on top of something else in order to sort of support it. In the commercial development that I was involved in, we actually did what is shown on the left. So we took the protein, put them into these polymeric structures, these vesicles. These are basically small spheres which has proteins in them, and that gives that whole layer a very high selectivity. So we're not really making this very thin film, because we did need to have this trade-off with robustness. And you can see on the electromicrograph down bottom left how it looks in sort of reality. And basically we made these membranes in a company that we formed a number of years ago. And this is basically what they can be used for. So they can be used for reverse osmosis, like you would know from normal desalination, for example. Forward osmosis is another thing where they can be used. You've probably heard about RO, reverse osmosis, in terms of desalination. That's sort of the application which comes to mind right away there. But forward osmosis is interesting. That actually allows you to do many interesting things, such as, for example, cold concentration. If you want to pull out water of something, you want to up concentrate it, but you don't want to heat it up, because otherwise that will destroy your product, then this is a very nice way to go. And then you could, of course, ask the question, why didn't people do that a long time ago? I mean, osmosis have been around as a scientific concept for more than 200 years, but that's just because it's very hard to make these membranes. So I think now the world is kind of opening up, where we can begin to also do these things. And as I said, we started the company in 2005, and it's been working for a long time now. But basically, these are the products. There are products on the market here that we can do this. So it's sort of really taking it out from the lab and actually now being able to make units and modules, things that people can actually use. That gives this superior productivity in terms of flux and rejection for these membranes. So this is not a sales pitch, but I just want to highlight this, that actually it's not just interesting fundamental science, and there's still a lot of loose ends that we need to figure out, but actually it is moving into becoming commercial products. So I'm to conclude, because I also would like to also leave questions time for you here, is that yes, it is possible to make these membranes. It's actually moving out of the lab. For the reverse osmosis membranes, you could say it's really the flux, the fact that you can get more water through at the same pressure. And for the forward osmosis, this fairly new technology, you have this ability to up-concentrate valuable compounds. There's still a lot of work to do, but I think this is definitely moving ahead, and it's moving out of the lab. I think there's one thing you should remember from my talk. It is that this is not just something which is sort of a nerdy science. It's actually beginning to become a real product out there in the world. I think the future we're looking into, I think this whole idea of using these artificially made structures will actually be more and more, we'll see that more and more. But again, there are also definitely some issues in how these things, they assemble and structure themselves in the membrane, which we still need to work on a lot in order to bring us forward. But I hope that I have given you a little sort of peek into sort of the lab and the development and production of these new type of materials, these new type of surfaces. And again, if you remember back to my very first picture with the biological membrane, there's so many different functionalities that we can actually look and be inspired from these membranes in biology and turn them into really interesting and also, I think, valuable materials in terms of new surfaces. So with that, I'd like to thank you for your attention here. And I know this was sort of a fast helicopter through the issues at hand, but I hope at least I have given you sort of a gist of what this new area, relatively new area of science and engineering can give us. So thank you very much, and I'll stop sharing and leave time for a few questions. Thank you.
Thank you very much, Claus, to put together this multidisciplinary knowledge in a very snippet manner within a succinct time frame. Thank you very much for that. It was really delightful to see that presentation. I have a very quick question, Claus, or rather, I'd
Sure.
like to have your thought or comment. This definitely seems to be an area where clearly, I especially like the molecular dynamics simulation video you showed. Would you like to comment how these atomistic simulations, which are often criticized, do not have the same length time scale with experiments, but particularly here, they seem to be very relevant, have guided the design of these membranes?
Right. I think what I think the first MD simulations, they really reveal these very high rates, because it's hard to actually measure single channel water permeability without being too technical today here. So in the beginning, people were discussing these things, and also the fact is that in molecular dynamics you can use many different force fields when you do this. So you still have an issue with actually what is the net sort of the free energy associated with the transport. How high is that transport barrier? And people have been struggling to. I think it's beginning sort of to line up a bit better now. But for sure, this is still a debatable issue. How can we actually, which model of water should we use? How should we treat polarizability and many of these things? So I don't think we should be carried too much away with this. And I think, on the other hand, that if you look into to this also, especially to guide the design of artificial structures, what is required for a narrow tube, if you want, in terms of lower the barrier for water and prevent also non-polar solutes. Maybe you have things like urea and other things that are not that much bigger than a water molecule, and how do you then make sure that they're not passing through your structure? And you can broaden that up and also look into something like DFT, in density functional theory, which of course is relying on something, or has to rely on something which is a bit more, structured and smaller in a way. But as again, I think that this is also an area where we'll see more, because we at the bottom line, we need to have these very thin structures. So the whole magic is happening over a stretch of where just a few water molecules are passing. So it is really narrow. We're talking about sort of the maybe 1 nanometer or less than that. If we understand that physics, that chemistry, to the extent we can build structures around it that allow this selectivity, also at the same time having this very high permeability, then I think we can move ahead. So I see that definitely as a strong driver for development of these, especially the artificial structures, in the years to come.
Thank you, Claus. We are very lucky to be on time right now. So if you are also available on the panel later on, we will do further questions.
Sure.
So we can now take a 10-minute short coffee break. And then my colleague, Professor Murphy, would introduce and start with Professor Margaret Stick after 10 minutes coffee break. So we can hope to begin sharp at 10:55, if everybody's okay. So a comfort break of 10 minutes, and then we'll resume again.
All right. Okay.
Yep.
Okay.
Thanks a lot. See you again soon.
You.
All right.